All right, it's 7 o'clock, so we're going to get rolling. Looks like all of you are in the Pear Deck presentation. So just like I've done the last few weeks, I'm going to be jumping back and forth between the Pear Deck screen, where you guys can interact with the screen, and the PowerPoint screen or Zoom screen, where I can actually write on the screen and you can watch it. So if I tell you to go to the Pear Deck screen, go there and you can enter answers and such. But if I tell you to look at the Zoom screen, come back there, and that way you can see what I'm writing. And as I'm working problems, you can see my solutions. Pear Deck won't let me write live time on the screen, so it makes it a little bit difficult for me to show you the solutions unless I just have pre-canned answers. All right, so we're going to get rolling. So today's topic is about energy and work. So hopefully you guys know that energy is just the ability or the capacity for doing work. We've talked about different forms of energy. Hopefully you guys are familiar with them. The main ones you'll see in AP Physics are kinetic, potential, a little bit of thermal. And those are really the only ones we're going to deal with in this course. There's also electrical energy, there's nuclear energy, there's some other types. But in this course, essentially, we're going to be talking about kinetic, potential, and thermal, which is just heat. We measure energy in joules, and hopefully you know a joule is equivalent to a Newton times a meter or a Newton meter. And we talk here's the types of energy again that we're going to talk about. First of all, there's a big category of energy we call mechanical energy. Sometimes it's abbreviated just ME. Mechanical energy is the sum of the potential and kinetic energies of either an object or a whole system, if the problem is talking about the whole system. So it's potential plus kinetic. Kinetic energy is the energy an object or system has due to its motion, it's moving. So there's two types of kinetic energy you need to be familiar with. The first one is what we call linear, or what your AP Physics formula sheet likes to refer to as translational kinetic energy. And to calculate that, it's just 1/2 mass times the velocity squared. That's for linear motion, not rolling, not rotational. There's also rotational kinetic energy, and that's equal to 1/2 times the moment of inertia, I, times the angular velocity. That's measured in radians per second square. So notice those two formulas are very similar because really inertia and mass measure the same thing. And then you've got linear velocity V, and then you've got angular velocity with that omega. So an object that like a tire that's rolling down a hill could have a combination of both of these because it's moving in a linear direction, but it's also rotating as it moves. So things that are spinning, or things that are, let's not say spinning, let's say things that are rolling and they're going in a linear path have both types of kinetic energy. We also talk about gravitational potential energy. Potential energy is energy that's stored in an object. Gravitational potential energy is energy that's stored due to an object's position above the Earth. And we usually notate it like so, mgh. So that's mass times acceleration due to gravity times the height above the reference point. Sometimes instead of h, you'll see delta y there because it's usually a vertical height. There's also elastic potential energy, which is the energy that's stored in a spring or like a rubber band. And we calculate that 1/2 K, which is the spring constant, times the amount of displacement. So that's like the amount of meters that the object stretched or compressed, and that's squared. So 1/2 Kx squared. All of those formulas are on your formula sheet. So just know what they are and how to use them. And we're going to get some examples of how to use them here in just a minute. We're also going to be talking about work today. So work is when a force acts on an object and it moves that object some distance parallel to the force. And we're going to come back to parallel in a minute. It looks like I've got some chat things popping up. I can't really see the chat bar right now because of the way I'm using the screen. So if you have a question, just unmute and feel free to ask. That way I won't miss it. So work can cause changes in mechanical energy. It can increase the mechanical energy in an object, or it can decrease it depending on the direction of the work. The formula we're going to use to calculate work is force times distance times the cosine of the angle theta. And in this case, theta is essentially the angle between the application of the force and the direction of motion. And we'll see how that actually plays out here in just a second. Work is a scalar, so it's just about magnitude, but it still needs a sign. The sign here is not so much about direction. Work is positive if the work acts in the same direction as the distance that the object moves, the direction that it moves in. And work is negative if the force acts in the direction opposite of the motion. Maybe the most important way to think about positive work is it's adding energy to the object that the work's being done on. So you're increasing the amount of mechanical energy in that object if you're doing positive work on that object. If you're doing negative work on an object, you're essentially dissipating energy from the object, probably turning it into heat or something like that. So positive work, you're adding mechanical energy to the object. Negative work, you're dissipating energy from that object. And notice in bold, work is only done if the force acts parallel to the direction of the motion. So you might have a force that's applied to an angle. And we're going to work some problems like this in a minute. So if you want to calculate the work, you could use W equals FD cosine theta. And I'm going to go to the PowerPoint screen now. So if you'll go back to your Zoom screen with me, if you're in Pear Deck. And let me pull up PowerPoint and show you a couple of drawings here. So let's say that we've got a box and we have some kind of rope attached up here to the box, and we're pulling upward and to the left on the rope. So some of that force is an upward force, and we'll call that force FA for right now. Some of that force is a force acting to the left on the box. So the box is actually going to move this way. That's the direction of the distance that it's going to move. So if we want to calculate the work, we would draw in like a horizontal here. This angle would be theta, the angle between the application of the force and our motion, like so. So if we wanted to calculate that work, we would just say force times distance times the cosine of theta. We could calculate a work. Now you could also do it by taking this force and you could resolve it into components. So you could break it down into a vertical component and a horizontal component. And in this case, since the box is moving horizontally, the component that matters and the only component doing the work is that horizontal component. So you could just do W equals FD, where that component is the F and the distance is how far the box moves. And that way you wouldn't have to worry about the cosine of theta. So you can do it either way. You can use FD cosine theta, or you can resolve the force into components and use only the force component that is parallel to the direction of motion. Either one works. And like I said, if you guys have questions, stop me. I'll be glad to answer them for you. All right, so we've got a question here. So let's go back to the Zoom screen now. And I want you guys to attempt to answer this question. So let me get on the correct screen. So it's asking you to draw a free body diagram for this problem. So I'd like for you guys to just read the question, and then anywhere on this slide, draw in a free body diagram for me and make sure that you label all the forces that you're drawing on that free body diagram. Take about a minute, see what you can sketch out for this problem. All right, so you guys were quick on that. So I'm just going to go, let me take a look at what you guys did first of all. So it looks like some of you were just getting started. You want to make sure that you label the forces. It's looking like you guys are still working on these. I'm going to give you about another minute to finish them up. Keep working. Doing good. So if you just joined, go to joinpd.com and enter the code you see on the screen there, ASEMXR, and that will get you into our Pear Deck presentation. I just had one more person enter, so if you just entered, please go to joinpd.com and enter code ASEMXR to join our presentation. And what we're doing right now is everyone is answering this question. And let me go back so that you guys who just joined can see it. So we're drawing a free body diagram for this specific problem. And I want to go ahead and go to the next slide and show you what the answer looks like. So this is what we should have seen. So we were pulling or pushing on that box. I think we were pulling on it with an applied force. So we're going to draw that force acting out from the center of the box, and it was moving toward the right. Well, the box has weight. Weight always acts straight down. In this problem, the box was sitting on just a flat horizontal surface. If that's the case, you're also going to have a normal force acting equal to, but opposite of the weight. So this normal force arrow that you see up top should be the same length as the weight arrow, and they should be completely opposite of each other. Also, you had a frictional force. Well, we know that the frictional force always acts in the direction opposite of the motion. So if the box is moving to the right, the frictional force should act toward the left. Now, I'm going to go back to the problem just for a second because I need to look at something. So it also tells us that we're applying a 50 Newton force to the right and a 30 Newton force. There's a 30 Newton frictional force. So when we're drawing our free body diagram, we want to make sure that we draw that applied force arrow a little bit longer than the frictional force arrow, because the lengths of those arrows can represent the magnitude of the forces. So the normal force and the weight, those should be the same length because they're the same magnitude force. The applied force should be a little bit longer arrow because it's a larger force than the frictional force. All right, so notice the next problem, same prompt, but this time we're asking for an amount of work. So I'd like for you guys to calculate an answer here. Go ahead and calculate and enter an answer. All right, I'm gonna see what you guys are thinking. So A or B is what you guys are thinking. So I'm going to go back to the PowerPoint for a minute. So look at your Zoom screen with me. All right, so we want to know how much work is done by the applied force. And we're going to be working from F equals FD cosine theta. So in this case, we're looking for the amount of work done by the applied force. Well, that force is 50 newtons. And the box moves a distance or a displacement of 10 meters. So D is 10 meters. What we've got to think about here is what's theta? Well, in this case, it's pulled across a flat surface. So we're assuming that the picture maybe looks something like this. Well, that means that the angle between the application of the force here and the direction of the displacement also here, there is no angle between those. So theta is 0. So we take the cosine of 0, which is 1. We multiply that by the force and the distance, and we come up with 500 Newton meters or 500 joules. So answer B is what we were looking for, and that looks good. All right, now let's back up to the Pear Deck screen, get to our next question. It's going to be the same prompt again with just a slightly different question. This should be a fast one. So go ahead and input what you think the answer is here on question number 3. This time we're looking for how much work is done by the frictional force. All right, so I'm looking at your answers. So I'm seeing a couple of A's and B's and a lot of C's. So I'm going to go back to the Zoom screen PowerPoint. So this time, again, here's our box. We know it's moving this way, but we know the frictional force acts back this way. And we know the frictional force is 30 newtons. Well, the box moves 10 meters, so that's the distance. The force is 30 newtons. But remember, the cosine of theta, theta is the angle between the direction of motion and the application of the force. So that's this angle. And that's 180 degrees. So what our work's going to look like is work equals our force times our distance times our cosine theta, which would be 30 newtons times 10 meters times the cosine of 180. Well, the cosine of 180 is -1. -1 times 10 times 30 ends up giving us -300 joules. So in this case, that work is dissipating energy out of that can. It's essentially turning some of the energy that the can had into probably heat. The frictional force does that. It dissipates the work. Negative work, remember, is dissipating heat out of an object or a system. Positive work is adding energy to a system. All right, let's go back to Pear Deck. And look at question 4. Again, same prompt. This one should be pretty fast too. So go ahead and answer what you think the answer is to number 4. Got one more person we need to answer. All right, everybody's answered. Let's see what you were saying. So most of you were saying D. 1 or 2 of you were saying C. So let's go back to PowerPoint or Zoom. And let's think about what's going on here. So again, here's our box. It's moving this way. In this case, there's our force. And that's the force of gravity. Gravity acts down. The force in this case would be the weight, because we're looking for the force of gravity, right? So it would be work equals FD cosine theta. The force would be the force of gravity, which would be the weight. So it would be 4 kilograms times G. It would be 40 rather newtons. The distance, 10 meters. But in this case, we're looking at the angle between our displacement and our force, and that's 90. And if you take the cosine of 90, I think you guys know what you get. You get 0. So cosine 90, or we could think of it as 270, either one works. And we end up with 0 work. Because remember, work is only done if there's a component of the force that acts in the same direction as the motion. And in this case, there's no component of the gravitational force that acts horizontally. Therefore, that gravitational force does no work. All right, back to pair deck. And that same idea should work on this one, so we're not going to waste a lot of time here. The normal force also acts at a 90-degree angle to the displacement, to the motion. So I'm hoping that you guys see that there is no component of the normal force that acts in the direction of the motion. And therefore, the correct answer on 5 is D. There's no work done because there's no component of that force that acts in the direction of the motion. So go ahead and mark D if you haven't already, just so that you have the correct answers marked. All right, and now I want you to try question 6. Notice this one's asking for the net work done on the trash can. So there's 2 ways you could do this one. One way we've pretty much already done. You can calculate the work done by each force and add those up. So we had 0 work done by the normal force, 0 work done by the gravitational force. We had, let's see, 500 newtons of work done by the applied force and negative 300 newtons done by the frictional force. So if you add all those together, you end up with 200 joules of net work. The other way to do it is just find the net force. So in this problem, the normal force and the gravitational force cancel each other out. So there's no vertical component. The 50 newtons to the right cancels out the 30 newtons to the left, and that leaves 20 newtons to the right. So our net force is 20 newtons, and that acts over 10 meters. And that direction, the angle between that force and the motion is 0. So it would be 20 newtons, the net force, times 10 meters, the distance, times the cosine of 0, and we would end up with 200 joules. All right, before we go any further, does anybody have questions on any of these first 6 problems?
I have a question.
Yes, sir.
To find the cosine theta, can you explain that again?
Yeah, so let me go back. I'm going to go back to PowerPoint so I can draw. So let's go back to our box. And let's say that our box is this, let's say this line represents the direction the box is moving in. And this line represents the direction of the force acting on the box. So the angle between the direction of motion and the application of the force, that angle is theta. So in this case, theta would be 90 degrees. On the other hand, if this one is still the direction, but let's say in this case, the force was acting this way, that angle would be 180 degrees. If on the other hand, the force was acting this way, we could think of that as 90 measured this way, or we could measure it as 270 that way. Either way, we're going to get the same answer. And then finally, if the direction was still this way, but the force was also applied this way, that angle would be 0. Does that make sense?
Yes, that makes sense. If since you said like if the force was being applied and you pointed the arrow downwards, would the theta be negative 90 or would it just be 90 still?
It probably would be more exact to go ahead and use 270.
Oh, okay.
But since you're doing cosine, they're both going to be 0, so it doesn't really matter. But 270 would be the more correct way to do it.
All right. Thank you.
Mm-hmm. All right, let's go back to Pear Deck. Then I think there's one more problem having to do with this prompt.
I got a question.
Sure.
For these type of question, is our calculator supposed to be in degrees mode?
Yeah, you should for this class keep your calculator in degree mode. I can't think of any exceptions to that for AP Physics 1. Keep it in degree mode. All right, so we've got, there may be 2 more problems with this prompt. So go ahead and see what you can do with question 7. And just to give you a hint here, you've got to use the idea that work equals to the change in kinetic energy. Work equals change in kinetic energy, the work energy theorem. Work equals change in kinetic energy. That's the idea on question 7. And I really want you to think of it. Well, I'll get to that in a second. Go ahead and keep working. I'm going to take a look at what you guys are thinking. So we're kind of all over the place on this one, B, C, and D. This is the hardest problem we've seen so far tonight. I want to go back to my PowerPoint now. So go to your Zoom screen. All right, so here's the idea. Told you before, we're going to think of work equals change in kinetic energy. And really, I want you to be more specific. I want you to think of this as net work. So it's the net work on the object or the system. In this case, we're talking about an object, a trash can. And that net work causes the kinetic energy of that system to change. Well, if you remember, we already found the net work, but we can find it again. The net work is going to be the net force times the distance times cosine theta. So if you remember, our net force was 20 newtons to the right. Our object moved 10 meters. And thinking of our box, so we were pulling it that way. That's our applied force. It moved that way. So the force and the direction of motion were the same. So the theta is 0. So our net work is the net force 20 times 10 times cosine 0. So our net work is 200 Newton meters, 200 joules. That's equal to change in kinetic energy. Notice that's delta kinetic energy. So we started off with an object that wasn't moving. So how much kinetic energy did the object have to begin with if it wasn't moving? Somebody unmute and tell me. Easy answer.
0.
Moving, how much kinetic energy does it have?
0.
0. So if we're finding the change in anything, how do we find that? What's the formula for finding the change in anything in physics?
Final minus initial.
Final minus initial. So we want to take the final kinetic energy. And remember that kinetic energy is 1/2 m v squared. In this case, what's the final velocity? That's what we're looking for, right? We're looking for the final velocity. And then we want to, that's, everybody agree that that's the final kinetic energy. We do have the mass, so let's go ahead and put in the mass. The mass was 4 kilograms. So that's final minus initial. Well, the initial velocity of this trash can was 0. So this all goes to 0. So that doesn't really matter. So we've got what let me put it down here where you can see it a little bit better. So we've got our net work, 200 joules, and that's equal to 1/2 times 4 kilograms times that final velocity squared, not to the second, not to the 2. All right, so if we simplify this just a little bit, let's go ahead and go 1/2 times 4 to get 2. Let's divide both sides by 2 kilograms. So we would end up with 100 joules over kilograms. And that's equal to V squared. So we need to take the square root of both sides. And when we do, we end up with positive 10 meters per second. So that's that net work causes the object to speed up and acquire a velocity of 10 meters per second by the end of the problem. Really big idea in this unit is that net work causes changes to the kinetic energy of an object. Big, big idea. All right, let's get back to Pear Deck. All right, so we finally moved away from that prompt. So let's talk power for a minute. Power is essentially a speed of doing work, a rate of doing work. How fast do you do work? Or we could think of it as the amount of energy, because work is really another way of thinking about energy, the amount of energy transferred per unit of time. It's a scalar. There's no direction for work, but we measure power in joules per second, which remember are also Newton meters per second. And that unit is given a special name. It's called a watt. So a Newton meter over seconds or a joule per second, that's what a watt is. Now I want us to go back to the Zoom screen because I want to derive some of these equations that you see down here at the bottom. So again, main equation, power is work over time, which really is just another way of saying energy transfer per unit of time. So these two really say the same thing. Remember though that work is force times distance. So we could rewrite this instead of work over time, we could write it as force times distance over time. And what I'm hoping that you guys remember is that distance over time, what is that equal to? What's distance over time?
Velocity.
Yeah, well, since it's distance, it maybe not velocity is probably not the right word, but speed. Speed. So power can also be written as force times speed. And that one, they'll kind of throw that one at you sometimes as a curveball because a lot of people just don't think of power being force times speed. But realize these two formulas that you see right here, exactly the same thing. Force times distance over time is the same thing as force times speed. All right, so while we're here, let's also talk about conservative versus non-conservative forces. So a conservative force is a force that converts potential energy to other forms of mechanical energy when it does work. Usually it converts potential to kinetic. And that could be a translational kinetic, like linear kinetic, or it could make something roll or speed up as it rolls. So it could be rotational kinetic energy, either one. Conservative forces are called that because when a conservative force is applied, the mechanical energy of the system is conserved, stays the same. As it says in the next bullet, the work done by a conservative force is path independent. The direction, the way it moves doesn't matter. And it only depends on the initial and final positions of the object. The conservative forces that we deal with in AP Physics 1 are usually either gravity or the force in a spring or rubber band, like an elastic kind of force. Those are really the conservative forces we're going to talk about in this course. Gravity and elastic forces, like in a spring or a rubber band. Non-conservative forces, on the other hand, change the amount of mechanical energy in a system as they're applied. So, and most of the time what happens is some of that energy is dissipated out and it's converted into either heat or sound or something like that, maybe even light, depending on what's going on. The work done by these non-conservative forces is dependent on the path the object takes. And the non-conservative forces that we deal with in Physics 1 are usually either friction or drag, which are almost like two sides of the same thing. So these dissipate energy from a system, they dissipate mechanical energy, and some of that mechanical energy is released as either thermal energy, heat, or maybe sound or even light. All right, we already talked about the work energy theorem, big idea. Net work causes changes in kinetic energy. If we're dealing with work done by conservative forces, we could think of work as the change in the final potential energy minus the initial potential energy. If, on the other hand, we're dealing with work done by non-conservative forces, work is usually equal to the change in the kinetic energy plus the change in the potential energy. An important note here. It's important to realize that kinetic energy term in that equation up above can be translational kinetic. It could be rotational kinetic energy, or it could be both. If we have like a tire rolling down a hill or something like that, it could be both. So realize when you're thinking about kinetic energy, it can be the translational and the rotational. And when we're dealing with potential, it could be gravitational potential energy and elastic potential energy. One or the other, or both, depending on the problem. All right, so here's another problem. And let's go back to Pear Deck before we do this. Let me get to the right slide in Pear Deck. Let's talk about this first. So oftentimes in physics, you're going to get graphs of force versus position, or sometimes it may be listed as force versus distance, either one. So if you have a graph of force versus position or force versus distance, you can find the work done on that object by calculating the area under the curve. Because really, remember, when you're calculating the area under the curve, essentially you're multiplying whatever's on the y-axis by whatever's on the x-axis. So in this case, that would be force times distance. But again, remember, the graph may be labeled force versus distance, or even sometimes force versus displacement. So if you have any of those graphs, force versus position, force versus distance, or force versus displacement, you can find work by calculating the area under the curve. That being said, here's an example. Sometimes you'll get messy curves like this. So on one like this, you may have to divide that area into several different shapes. You may have to divide it into multiple rectangles, triangles, whatever it takes to calculate the work. If it's above the axis, the zero line, it's positive work. If it's below the axis, negative work. That's important. So we have from 0 to 10 meters, from 0 to 9 meters really, positive work is being done on this object. And then from 9 to 20, negative work is being done. So when you're calculating the areas, that sign does matter. That being the case, I want you guys to try this problem. So try to find the change in the box's kinetic energy between 0 and 4 meters. So see what you can do here. And I just want you to write in the answer on the screen. This one is a multiple choice. Just write in what you think the answer is. And you can draw on that graph if it helps you to calculate the area under the curve. Take about 2 minutes to see what you can do with that one. All right, so I've already got lots of answers. Let's see what you guys are thinking. All right, so our answers are kind of all over the place. So let's go back to the PowerPoint screen. Think through this one. So this one is asking for what is the change, my grammar is all bad there, in the boxes. That should be BOX apostrophe S. Box's kinetic energy between 0 and 4 meters. Well, we've got to know two things here. First of all, we've got to know that the area under a force versus position curve is work. We also have to remember that work equals change in kinetic energy. So if we find the work, we've got the change in kinetic energy. You had to know this to be able to work this problem. So the easiest way to do this is take a straight edge and let's make a rectangle here and a rectangle here and just calculate the areas of those rectangles. So to calculate the area of a rectangle, it's just length times width. So for this one, we would be 2 wide and 40 tall. So the area of this one would be 80. And that's 80 Newton meters because we're taking these units times these units. This one is also 2 wide from 2 to 4, and it is negative 20 down. So 2 times negative 20, negative 40 Newton meters. So to find the work, we just add those up. That's all the area under the curve. So 80 plus minus 40, we end up with 40 Newton meters or 40 joules of work. And remember that net work equals change in kinetic energy. So 40 joules or 40 Newton meters is what we were looking for on problem 8. All right, so let's go back to Pear Deck now. I want you guys to go ahead and attempt this one as well. See what you can do with number 9. Tell you what, let's get number 9 for now. That one's got a wrinkle in it that we haven't talked about yet. If we have time, we'll come back to 9. Let's try 10 first. So go ahead and see what you can do with 10. Really important problem here. And I'll give you a hint. This is really an energy problem. And you're going to need to think about the law of conservation of energy here to work this problem. I'll show you how to do it in a second, but that's my hint. Law of conservation of energy. There's no friction in this problem, so energy is conserved. Mechanical energy is conserved. Let's put it that way. going to take a look at what you guys are thinking. So I'm seeing D's and B and C. All right, so it turns out D's not the right answer. So let's go back to the Zoom screen and think about this one. So we've got something like this. So we've got an inclined plane, no friction. Think of a box being up here, like so. There's the horizontal. The length of the inclined plane from like tip to tip, that's 10 meters. It's angled at an angle of 20 degrees above the ground. So that means this angle right here is 20 degrees. What is its speed? All right, so you got to think of this problem this way. At the top of this incline, up here at the very top, if that thing hasn't started moving yet, what kind of energy does it have up at the top of the incline? Somebody help me out.
Gravitational potential. Gravitational
potential. And that's the symbol we usually use up at the top. And remember, that's equal to mgh. So all of the energy, all of the mechanical energy in the system at the top is mgh. Down here at the very bottom, once we get exactly to the ground, what kind of energy do we have?
Kinetic.
Yeah, translational kinetic, right? There's no rotational kinetic here. This is just 1/2 mv squared kind of kinetic, translational kinetic. Are you guys in agreement that the potential energy at the top ought to be equal to the kinetic energy at the bottom? Does that make sense?
Yes, sir.
No friction, so those ought to be equal. So let's set them equal. mgh equals 1/2 mv squared. All right, do you guys see that the mass cancels out? We don't need to know the mass because it cancels out. It's on both sides. So I'm just going to erase it like so. But notice we still have two variables that we don't know. We know G. We know G is 10 meters per second square. We don't know the height. We don't know the speed. We're looking for the speed. How could we find the height?
10 times the sine of the angle.
Yep. So we could take this incline and essentially make it into a triangle. And we could solve for this height. So we could say sine 20 equals opposite, which is h, over hypotenuse, which is 10. So h would equal 10 sine 20. And calculate that out. That equals about 3.42. That's h. So I'm going to erase a little bit here so I have some space. And before I plug in the 3.42, I'm going to go ahead and simplify my formula here. I'm going to go ahead and solve it out for V. So I'm going to multiply both sides by 1/2 to get rid of, or by 2 rather, to get rid of the 1/2. So that'll make this go away. And we'll multiply by 2. And then to solve for V, we would take the square root of both sides. And now we just plug in what we know. So it'd be 2 times 10 times our height. Take the square root of that whole thing. And we end up with about, so I did something wrong there. Let's try that again. So about 8, I got 8.27. Anybody have an idea why I'm getting 8.27, but the answer is 8.19 here?
Because you use 10 for the acceleration of gravity instead of 9.81.
Exactly. So when I worked this problem out originally, I was using 9.81 as G. Remember though, on the AP Physics 1 exam, G is always 10. They keep it simple. So just get into the habit of using 10 meters per second square for G. I've been teaching physics for so long, sometimes I still revert and use 9.8, but use 10 meters per second square always for G in this particular course. Does this question make sense now? Any questions? Let's see, we did that.
I actually have a question about the initial energy. So for that UG, that's potential energy, right?
Right, that's gravitational potential energy.
Okay, that's all I need to know.
Yes, sir. Gravitational potential. So just a little bit about conservation of energy. So the total amount of energy in a system is always conserved, no matter what. But oftentimes, especially in AP Physics 1, we're not thinking about the total energy of a system or an object. We're thinking about the mechanical energy, which, remember, that mechanical energy only takes into account what two things? What two things correspond to mechanical energy?
Potential energy.
Yep.
And kinetic.
Exactly. So when friction is involved in a problem, friction or drag, mechanical energy is not conserved. Because what's happening to some of that mechanical energy if there's friction or drag involved?
It's like transforming into like maybe thermal energy.
Yeah, almost always it's going to heat, thermal energy. But if there's no friction or no drag, which is usually the case in this course, AP Physics 1, then mechanical energy is conserved. So mechanical energy is conserved when there's no friction or drag. If there's friction or drag in a problem, mechanical energy is not conserved. So you can't go that route. But most of the time, when you're getting an energy problem, you can think of mechanical energy as being conserved. Just make sure there's no friction or drag involved in the problem. All right, we're going to end today by looking at this problem. So I'd like for you guys to take just a minute or two and go ahead and read the initial prompt, look at the picture, and then read part A. Take about 2 minutes to do that. I'll see if I can move this. All right, so big idea is the block starts off right here at 0. And then we push on the block and compress that spring. So we push it in the negative direction, compress it. So when it's at this point, it's not moving, which means it shouldn't have what? At negative D, it's not moving, so it doesn't have what?
Kinetic energy.
Yep, so at this point, kinetic energy is 0. At this point, the potential energy would be the elastic potential energy. And how do we calculate that? Anybody remember how we calculate elastic potential energy?
MGH.
No, that's gravitational potential energy. In this case, we're looking for energy in a spring.
It's 1/2 kx squared.
Exactly. Where K is the spring constant, which would have to be given to you, and it's not in this problem. It's essentially how stretchy or hard to compress a spring is. And this X is the distance of compression. So in this case, our X would be minus D. We don't need to calculate it in this case. We just need to think about, at this point right here, 0 kinetic with some elastic potential. All right, then we're going to let it go. And when we let it go, we know the spring is going to shoot out this way. And as it shoots out, what happens to the amount of potential energy as the spring shoots out?
It turns into kinetic energy.
Right. So the potential energy goes down as kinetic energy goes up. So let's go to the graph here and see what happens. So would you guys agree at right here, negative D, the kinetic energy should be 0, right?
Right.
So as we move this direction, if we're drawing kinetic energy first, kinetic energy ought to go up, right? What kind of shape should it go up in?
It should be like a parabola and it should be the highest at 0.
All right. So why are you saying parabola? Because a lot of people would have said a straight line there. Why do you think it's a parabola?
Because it's not constant, so the kinetic energy changes because it's going from potential to kinetic and then back to potential.
Okay. So you said an important word. It's not constant. What's not constant here?
The value of kinetic energy. The mechanical energy is the same, like the total energy is the same, but the kinetic and the potential are always going to be opposite.
Okay, but what's actually causing the shape to be a parabola though? It's not so much the kinetic energy here that's not constant.
Because it's
What
squared.
about the spring that's not constant?
The block's gonna end up going back, but not all the way to its original.
Yeah, it's all about the force. If you guys remember Hooke's law, F equals kx. So this is like the force in a spring, the restoring force of a spring, and it's equal to that spring constant times x, which is the distance of compression. So as the spring gets back closer and closer to equilibrium, this x gets smaller. Where x gets smaller, the force gets smaller, which means the acceleration of that object also gets smaller. Because the force isn't constant, the rate of increase of kinetic energy isn't constant. It's more of a parabolic kind of shape. So we ought to draw something like maybe, whoops, that's not very good. Let's try that again. Maybe something like that. And that's just showing us that kinetic energy is always going up, but it's going up fastest. Wait a minute, that's not right. What did I do wrong there? Should it be a concave up or a concave down parabola?
Concave down.
Concave down.
Should be concave down, right? It should look something more like that. And the reason it looks like that is because the force at the beginning is the greatest, right? The spring is compressed the most. That means X is the greatest. That means this force is the greatest. And then as we get closer and closer to 0, which is where the spring's not compressed at all, that force decreases, decreases, decreases. All right, what happens after we pass 0?
Goes back down.
Goes back down. Let's see it. So let's read something here. Let's go back to the prompt for just a second. So it says the block's released at x equals 0. The block enters a rough part of the track, which means what kicks in at that point?
Frictional force.
Frictional force. And from 0 all the way out here to 3D, what kind of shape should we show as we're drawing the kinetic energy in? We know it's going down, but is it going down in a parabola? Is it going down in a line? How should we connect this point to this point?
I feel like it would not be like touching the line, but like it'll be starting to even out with it.
You're saying you don't think it's going to get down to 0 kinetic energy?
No.
Well, okay, so eventually, let's see. Let's go back to the prompt for a second. So it says it comes to rest at position 3D. So comes to rest means that it's stopped, right?
Mm-hmm.
So if it's stopped, that means it has 0 kinetic energy. So it does need to drop all the way back down to the 0 line. So that's where we need to end. But my question is, how do we connect this point to this point? What kind of shape should we use to connect those 2 points? Parabola or a line?
Parabola?
It should be a straight line. And the reason it should be a straight line is that what's constant between those 2 points?
Acceleration?
Acceleration, because what's constant?
Frictional force.
The force. The force is the frictional force, and it's the same all the way from 0 to 3D. Does that make sense?
Yes.
So this line's our kinetic energy. Now we got to draw the potential energy curve. So over here at negative D, where the spring's compressed, where should that start at? Where should our potential energy start?
At its highest.
Yep, it ought to start up at the highest, and we don't know what that highest is. Let's just start up here somewhere like this. And then as the spring compresses, or as the spring stretches rather, what happens to potential energy?
It'll go down.
It goes down. And how are we going to show that?
Is it the opposite parabola?
So yeah, so it's as it gets to 0, as it gets here to this point, the spring's not compressed anymore at that point, right? So potential energy ought to be 0 at this point. And we got to connect it with a parabola again, because what's not constant between here and here? What is not constant between this point and this point?
The acceleration.
The acceleration, because the force isn't constant, right? Because of this whole Hooke's law thing. So when we connect these, we ought to have a curve that looks something like that. So a concave up kind of thing, showing us that the potential energy decreases the most at the beginning, and as the force gets less, it decreases more slowly. And then it gets to here. What happens from 0 all the way to 3D to the potential energy?
It will be increasing.
Now wait a minute. So when the box gets here, it loses contact with the spring, right?
Mm-hmm.
Which means the spring can't push on it anymore. So
So
what happens to the spring?
there will
Once
be,
the box leaves the spring, what happens to the spring?
it's not
It goes back to equilibrium.
Yeah, it just goes back to equilibrium and sits there. And the box is on the ground, which means what kind of potential energy, how much potential energy does the box have at that point?
none.
None. So we ought to draw a straight line right here along the x-axis like so. So this is our potential energy graph. This is our kinetic energy graph. Does that make sense? So from a prompt that looked simple, there was a lot of thinking that you had to get there. Now, you didn't have to get all of it right to get points. It turned out you got a point for getting this section right and showing that that was a line. You could get a point for showing that this was just a straight line at 0. And then you could have got points for showing these parabolic shapes over here on the left. But you did have to show those as parabolic shapes to get those points. So that was a little bit more complicated. And there you can see it. This is actually straight off of the scoring guidelines for the question off the AP Physics exam.
Sir, can you explain one more time why the potential energy stays just flat against the x-axis?
Yeah, so at this point, let's go back to the picture. It might be easier to see. So when our box is back here, there's potential energy in this spring, right? When we let it go, the box shoots out. When we get here, the box leaves the spring. So at that point, the spring is just stretched out. It's uncompressed. It's where it's at its equilibrium position. So if you just have a spring that's not compressed or not stretched, think of it this way. When that spring is here, At this point, what's x?
It's 0, so I guess it
Zero.
cancels everything.
So when x is 0, the potential energy in the spring is 0. And since the box is now just sliding across the ground, it doesn't have any gravitational potential energy either. So there's no elastic potential energy in the spring. There's no gravitational potential energy in the box, which means the total potential energy is 0.
So the reason it doesn't have any GPE, is that because there's no change in height? Because of the
Right.
MGH?
It's on the ground. It's at ground level. The height would be 0 as well.
Okay.
Does that make sense?
Thank you. Yes, sir.
Ma'am. All right, so we're already over time, so I think we're going to call it there today. Next time we may pick up and answer the last couple of parts of this question, because this is a really, for what looks like a simple question, it actually goes pretty deep into a lot of thinking. So we'll start next time with this, and then we'll pick up with probably the next unit we'll look at will be gravity and maybe some uniform circular motion. But we'll do this again next week, same time, same place. Thank you guys for being here today. I'm going to end the session. You should get a Pear Deck takeaway in your Google Drive account, and it should be under shared with me in your Google Drive account. If you don't get it, just get your teacher to reach out to me, and I'll be glad to send it to your teacher.